So when I started my time at Losmonk, which was about 5 to 6 months back now, the problem that we started with was, can we just take state-of-the-art reasoning LLMs and can we get them to go from a high-level research idea to a research paper? Our inspiration when we started was a bunch of papers that had already come out. Sakana had already sort of had their first peer-reviewed paper accepted at ICLR. Google had built an AI co-scientist, which was also very heavily human involved, and they'd also sort of released an early release version of Alpha Evolve and worked on, if I'm not wrong, some bin packing problems. So those were some of the inspirations that we started with, but then there were clear constraints that we wanted to keep in mind because we did not want to do something that had been done before. So one of the constraints that we set out was with minimal tools. For something like Alpha Evolve, for instance, there's a lot of complex engineering. It's fairly simple, but it is sort of a lot of scaffolding. We did not want that. We wanted it to be a simple agent that can just go from an idea to a paper. And when I say minimal tools, we also made sure that we constrained it to the tools that most coding agents currently have. So these are mostly read, write, list, and grep, right? So it's like, hey, agents, with just these tools, can they go from an idea to a paper? Second constraint, minimum scaffolding. Again, we did not want a lot of sort of meta engineering going into the process. So for example, even in Sakana's paper, when they sort of use a aid-like node-based system, they still do some meta engineering wherein nodes are pre-categorized into hyperparameter tuning, ablation studies, etc. Right? So there's already some domain intelligence that has gone into architecting the system, which was a constraint that we did not want to keep. With high autonomy, when I talk about autonomy, the important thing is if you look at a lot of these papers, the problems that are actually pitched to LLMs to solve are picked by human beings. And there actually a lot of time spent on framing those problems in a way that LLMs can make sense of them. And it turns out that it works brilliantly when you actually spend that time up front. But what we wanted to do was that we wanted it to be as autonomous as possible. So even, let's say, coming up with the idea, to which idea to work on, to actually spelling out the idea into hypothesis, absolutely minimal human intervention. And lastly, little domain intelligence. So for those of you not familiar, I am not a scientist, I'm not even an engineer necessarily, I'm not even a machine learning fanatic, one would argue. I'm just a generic chief of staff from early stage startups in Bangalore. So that was the constraint that was already built into the project, that there's absolutely no domain intelligence. I cannot force the LLM to do something I don't know how to do. Turns out that the answer to the research question is yes, somewhat, because like all good science, there's always a somewhat. But moving on, what did the system end up looking like? And the way that I structure the presentation is I'll just do a quick overview of the system, what we did, and then we'll talk about failure modes and general comments that we came up on. So the system ended up really just being a 6-prompt workflow, a 6-agent workflow if you're that way minded. It had access to modal compute, a sandbox using modal labs, and it also had access to modal storage. The 6 agents or prompts, as you'd like to call them, were idea generation, hypothesis generation, experiment planning. All of this went into Claude Code, and Claude Code sort of did the coding and the execution. We had an output evaluation agent that took in the output from Claude Code and then reviewed it. If the output was sufficiently, approved, and we can talk about what did the output evaluation agent do specifically, it went into paper outlining. Alternatively, it went to a revision agent. And you can't see the loops here, but the revision agent would go back to either one of these 3 stages. Either the idea gets revised, or the hypothesis gets revised, or the plan gets revised. Right. So that was sort of the system. There was a lot of context involved, right? So each of these agents were actually storing outputs within one repository, and every agent had access to all the files in the repository, and in some sense we had to actually instruct them to go through all the files, which is also a failure mode that we can come to later. The ones that have a star on them, which is idea generation, hypothesis generation, and revision agent, also used an external reviewer, right? So, and when I say external reviewer, I'm not talking about reflection or something. It's like an external agent, a different model that's reviewing the work. So that was sort of what the system was. We tried 4 ideas, right? So we picked up some domains. As you can see, the first one was multi-agent RL, the other 2 were world models, and then the last one was AI alignment and safety. We tried 4 ideas, 3 of them failed. It's uncertain whether it was the LLM or me which led to the failure, but since the LLM is the primary author, we'll just blame the LLM. But 3 of them failed, and 1 of them made it to the paper stage, and that is the paper that we submitted, and it happened to be accepted at the conference conference. Something that I'd like to note is that the expert feedback, so one of the things that we did do, though we set up the constraint on high autonomy, we did want to make sure that we're not wasting compute. So whenever there was an idea that we came up with, we actually sent them to the primary authors of the papers that inspired that idea and got feedback on, hey, do you think this is something that we should actually pursue? Will this push the field forward? Thankfully, all the ideas generated received a fairly positive response from the experts. None of them were called out as, too out of the whack or something. All of them were came up with positive feedback. The only one that got a little bit of a negative feedback was the first one, and that was also more of a feedback on how their work had been interpreted and not so much on how we were proposing to build on top of it. But yeah, so the final idea that made it all the way through was semantic entropy as jailbreak detector. And this is what the paper looked like. For people that are interested, we can talk about it in details, but the paper essentially was, hey, can we use semantic entropy as a measure for classifying harmful and peaceful prompts? Turns out you actually can't, because models respond fairly consistently, and entropy doesn't serve as a good enough signal for you to be able to identify if the prompt is harmful or peaceful. So that was the primary finding that got accepted. If you look at the reviews, so there were 3 AI reviewers in this conference and there was 1 human review. It was all borderline accepts, heads up, so it wasn't like a 5 or 6 for those who are familiar with how conference ratings are done. But even the human reviewer was a borderline accept, which I took as a good sign, that, hey, there's some merit into the work generated. And the reviews, though they called out that the work was not expansive, and that was primarily the negative limitations, which is hey, the scope of this is fairly limited, you haven't tested out more models, you haven't tested out other data sets. The positive thing was that all of them called out that these are very strong empirical results. So the experiments that were done, the data that was generated, the analysis that was done was empirically very, very sound, and also really good negative results, right? So while we did not necessarily propose a better jailbreak detector, we did sort of prove that you can't use semantic entropy as a measure of one. So that was sort of the output. I can get into the failure modes, but any questions so far, just in the interest of time? Yeah, go for it. I'll take 2, okay, yeah.
When does the human, do you just spin it off and it just writes a paper and finally use it, or what all steps are the human connected?
Yeah, I mean, that's a great question. Different ideas at different sort of level of human intervention, but to be fair, it was quite a lot like what you said, which is that, hey, I had a bunch of Colab notebooks. I just ran all of them one after the other. And the only human intervention, if I was to come back to this, the only thing that required a lot of human intervention was sort of perhaps the Claude Code bit. And that was also when I say human intervention, it's 2% human intervention, which was mostly hey, do you really want to do this now? Why don't you do this step later? That's it. Or it would be me prompting Claude Code to be oh, is this the best way forward? Why don't you consider 3 more, right? So it was mostly prompting when it came to the human intervention as well, to try to get the LLM to solve the problem, as opposed to, let's say, me offering a solution. Because again, I'm barely new to the solutions.
You didn't contribute anything to the idea or hypothesis?
Oh, nothing at all. Nothing at all. The only thing I contributed to the idea and the hypothesis and experimental planning was just reading them and seeing if they made sense to me. That's about it.
Nothing in writing a paper?
So to be fair, the most human intervention, which is again 5% or so, went into the actual writing of the paper. Sadly, that's not on the slide, because, and I'll talk about it, one of the failure modes that we identified is also that there's a lot of overexcitement in the eureka instinct in LLMs, which is hey, if you give them results, they will just read them to be mind-breaking, the best thing that has happened in the history of science. So that was sort of the amount of human intervention I had to come in and be okay, can we take it easy on those claims, because that's not true. So yeah, that was mostly, yeah, exactly. Hey, chill out. It's just a normal paper. We didn't solve physics. Yeah.
So you work with the context time problem.
So sorry.
How do you work with the context time problem? Let's say if you have a long-ass paper.
Yeah.
Then you have to also manage the context time shouldn't just be summarizing, because you also then say results of a past experiment or whatnot.
Yeah.
You have very strategic papers.
Yeah.
But it's something of your overall investment stock tools of action.
Yeah.
Stock tools does it by itself.
Yeah.
It backs up US with this already. this long-range task?
Yeah, so I didn't do any context management on Claude Code bit, the actual coding and the experimentation, so that was mostly sort of Claude doing it on its own, like deciding when to compat the conversation. Right. What I did make sure for context management is that, hey, if you can see the lists of files, like so for every Claude Code session, there was a log being outputted, etc., which Claude was writing for itself, and I had a little bit of a prompt where like make sure you mention all the decisions taking, all the mistakes you ran into, errors you ran into. So that was on the Claude bit. Other than that, again, there's no complex context management, scaffolding, or engineering here. It's literally just these documents in the repo. Each prompt, though, for the agent included like a guideline section, which sort of mentioned that, hey, you have to go through these files before you actually start doing whatever the task is, etc. So I did direct the LLM to sort of open relevant files, but that was it. Like no fancy context engineering. Anything else? Yeah.
Search for results, was it attached to
So all the agents, other than the middle, is like sort of 2.5 Pro, Gemini 2.5 Pro, which is like sort of a context thing. Yeah, does that answer your question?
No, so this is a data you basically need to run it on multiple event steps and so on.
Yeah.
Was that the database source?
Yeah. So for this paper, like the paper that got accepted, it essentially had two data sets that we sort of ran like our proposed method on, etc. So all of that was done by Claude Code.
Multiple sessions of Claude Code?
Yeah, multiple. Like, I mean, yeah, I haven't listed them, but at least like I would say upwards of 20, 25. So I had like about 20 of those code logs, files, etc. So 20 would be a fair number. Like, anything else? Or we jump? Okay, yeah.
When one session is started, how long it takes to write a paper with it?
I mean, so it wasn't run in one go in any way, wherein like, hey, Claude Code was just sort of going ahead and coding, etc. and everything. That was sort of the other human intervention, I guess, that, hey, I'm tired looking at Claude doing something for today, so let me stop it here, right? But again, I would say you could easily do it in like, I mean, I did it over like 15 days for each idea, right? You could easily pull it down to like 3 days, 4 days, if that's the only thing you're doing with your day, yeah. Like, okay? Yeah.
What was the starting point? Like, what was the input for the idea generation?
Yeah, so that's a great question. So the way that we did the idea generation, like again, minimal scaffolding. So the constraint that we set was we'll do paper mashing, which is like we took two papers that had been accepted at a conference and then just like sort of asked the LLM to mash them together and come up with a new idea, right? Yeah.
I have a question. The question is just how long does the Claude Code run, because it has time of issues.
Yeah.
So how will you able to start the extent? So if it is going on after some time, it faces some bugs.
Yeah.
If it's like, oh, I give up right now. So the attack also happen, or was it only your own intervention to stop it for today and then really get it?
Yeah, I know that happened a lot actually. That's a great question, right? So one of the, I mean, sadly it's not written in a very good way, right? But there's a difference between sort of, actually it should be in the design takeaways, I think, which is like, hey, separate generation and execution. So I did not run into timeout errors with respect to the actual code generation anywhere, particularly, like, because that sort of happened faster. I ran into a lot of them when I was executing the code, right? So for example, if there's a training loop of like 1,000,000 steps, that will take like 4 hours and Claude will time out. And one of the main failure modes was that in those situations when like sort of the Claude code is timing out, it will just reward hack and end up sort of, trying to drift the implementation. So it will just be like, oh, let me implement something simpler because this will be faster and I can get done with it in this 2-hour session, right? The way that I got around it was that we built a lot of like sort of context artifacts around what had to be implemented, and we kept enforcing sort of checks on what the implementation was. And after a certain point of time, I stopped running into them because we also started running those long tasks on like a detached function on modal. So it wasn't even as if we were like requesting Claude to keep a track of that task. Right, like Claude was just moving on to the next task, but that ran in the background. And in general, I think those timeout issues have also started to be addressed by Claude code itself, where you can sort of, just run it as a background task. It's gone up from 2 hours now to something more. So yeah, like, I hope that answers your question. Okay, sort of, so I have, like, I'm almost on time, right? But like, sort of, I'll share the decks super quickly. Failure modes we observe, bias on training data. LLMs will just default to what they've been trained on. If a library is out of fashion, they will still use that library and believe it is the right thing to do, even after you've told them, hey, go to the internet, there's a newer version available, don't use this one. So a lot of bias on training data, implementation drift, which is in the case of time or in the case of reward hacking, it will just implement something completely different from what you're asking it to implement. Memory and context issues, is self-explanatory. Overexcitement I've spoken about. Lack of sufficient domain and tacit intelligence. I would like take a minute on this, right? Which is that hey, you have to make sure that the prompts are super specific, right? And that comes from sort of domain tacit intelligence, right? What this means is, for instance, in any idea, what are the metrics that you even need to record, right? Do I record just the main ones, which is like, oh, total reward over a particular episode, or do I actually also record all the rollouts? Do I want to save that file for like later reference? Do I actually want to record mean average reward over like 10? So how do you decide what these metrics you're tracking in a particular experiment are, or what the process to run a particular experiment is? These are like things that scientists learn like over the course of their career, and they're not very well documented anywhere in a meaningful way. So there is a lack of that, right? If you ask LLM to come up with an RL experiment, it will only record the reward and tell you whether it's been successful or not. But any scientist will tell you that that's not the right thing to do, because the reward can be looking one way while the experiment could be doing something completely else. So that is something that you have to put into the prompts. Again, thankfully I didn't have any, so I just used the LLMs for that bit as well. And turns out that you can build like verifier loops that actually get that sort of domain intelligence into the primary prompts that you're feeding into your scientist system. Learnings and design takeaways, you want to start abstract and ground later, right? So something like the library issue, right? Like, so if you ground on a library or a data set right at the idea stage, you're going to end up with that decision throughout the pipeline, and you're going to like run into erroneous loops, which is going to be a problem. So when it comes to hypothesis generation, idea generation, you want to keep it as abstract as possible. You want to keep it focused on the problem statement. You want to keep it focused into the literature, as opposed to going into the specifics of implementation. It also comes from how these LLMs are trained, because they're trained for getting work done. They're being trained for agentic work, coding work, etc., where they're incentivized to come up with the specifics as soon as possible and get started. Whereas in science, that might not be the best thing to do, because you want to spend some time in the problem space and figure out what's happening. Plan for failure and recovery, right? So you have to tell the LLMs to make at the planning stage itself, observability, as in the case of like that training loop, the tests that need to be written for each particular module of the entire thing, ensuring that the LLM, let's say, prints out the data set format and reviews what the data set actually has before writing code on top of it, etc. So you have to basically, as a scientist, sit back and think of all the possible failure modes that you can think of and try to accommodate them at the planning stage itself, if you really want the AI agents to be able to execute autonomously, because otherwise they will run into some error and you will have to step in, which was one of the constraints that we set out at the start, that I don't want to be stepping in. Verify everything. So this is something that, I mean, Ayush, perhaps Ayush and Shikhar can talk about to all of you all later if they end up here, but you need to, at every stage of the pipeline, you need to build a verifier, right? And this is not just a verifier for like, oh, whether you're correct or not. It's also a verifier for, is this most recent? It's also a verifier for, is this falsifiable? Is it executable? Basically want to like take the scientific workflow and build a verifier for every step of that entire workflow. And you also want to separate process and outcome, right? So it could be that your total reward is seeming to go a certain way and the experiment is successfully executed, but the agent actually did not build a reward network, a critic network at all, because it was in a rush and it sort of reward hacked there, and there's a full fake critic network that's built out, right? So that's why you also want to verify the process and not merely the outcome, right? And yeah, you need to separate out the code execution, code correctness from the scientific significance of this, etc. Because it's very easy to look at like sort of a bunch of experiments run by the LLM and be like, oh wow, we did a bunch of experiments. But if it doesn't move the field forward, if it's not fair, if it's not significant, it doesn't lead to anything. It's just, you're using it as a coding agent. In that case, it's not a scientist. So you do need a measure for scientific significance separately as well. Log like a scientist is self-explanatory, right? I think just 1 second on this as well, which is like, what I realized is that, hey, when you have to get an AI scientist to decide what to do next, what you need access to is not in the papers, right? So when you look, most of the AI science work is happening off of the final papers, but what makes it into the paper is essentially what the scientists know is correct. What doesn't make it into a paper are the 5, 10, 15 different trajectories that the scientist went on and realized that they were wrong and narrowed down to the one that made it into the paper. So a lot of that data is missing, like from the internet in general, and the closest that you can come to recreate in that sort of space is giving your agents a lot of context space to write and explore and think and be curious, and then get them to make a decision. So yeah, that's about it, right? I think we're on time, right? Sort of, are we done? 15 minutes we're done? Like, or can I take a minute? Like, yeah. Sorted. So I do want to so we've done this experiment. We know that LLMs can do science. We know that somebody who's not an ML scientist or an engineer can use LLMs to do science and get their papers accepted. Right. Why is this important? It's important because AI for science is just becoming a thing, and science is more and more critical in the future. A lot of software and a lot of these things which have driven a lot of the world and their capital in the past are sort of becoming replaceable, and science is sort of still a frontier that we have a lot to work on, and there's a lot happening, right? So you can see OpenAI is now building building a platform for science. Claude's already announced a bunch of platforms and integrations for biosciences. There's companies like Potato that are building specific LLM-led agents for protocol design and execution. In the biosciences, again, there are people that are going the slightly more symbolic and formal way, wherein they're building sort of mathematic reasoners and a lot of the work that Aritra is doing that Paras spoke to you earlier about. Right, so there's a lot of money and a lot of attention going into building agents for science and AI for science as a whole. Super excited about the potential of it, because do strongly believe that how science is done is being rethought from first principles. And while we've had the baggage of whatever Indian government decision making in the past, in some sense with respect to AI-led science, we're all starting from scratch, and there's a lot that can be done, and there's no sort of necessarily baggage from history that we have to carry forward. What are some themes for everybody who's here, themes that I'm excited about? Definitely for the next 3-4 years, I'll say we'll need some experts in the loops. I don't think, we're right there right now where we can just let an LLM agent go ahead and sort of be a research intern at Lost Funk, for instance, so you do need expert in the loop, but I'd put it at the next 2-3 years, honestly, because we're already seeing insane amount of progress. Very excited about domain and capability specific language models, right? You're seeing this all over the place. You're seeing people doing this for bio, seeing this happen for protein, you're seeing this happen for material discovery, you're seeing it happen for nuclear fission design. Somebody mentioned the aircraft bit, bunch of stuff happening there on Verilog, automation through LLMs and jazz. So super excited about this. Need to solve memory. I think this is generic to a lot of long duration, long horizon tasks. Need to build specialized tools, need to collect more expert trajectories. Tying back to what I said, which is we have no data around how do scientists actually make decisions. It's just not on the internet, it's not written down, it's in research journals that are maintained by scientists on their laptops or on their deck. Until you have that data, you can't actually necessarily build a large language model as they're built today to make some of those decisions. So I think we will see a lot more of this in the next 2-3 years as well. A lot of these data sets coming out, expert trajectories, which showcase how decisions are made by scientists, not at the final stage of the paper, but over the course of the messy middle and the scientific process. And this we can talk about this as a high-level thing, but I generally think everybody here, it would be great if we shy away from the great genius theory, right? When I talk about LLMs doing science, everyone's like, oh, will it come up with relativity? I feel like that's a stretch for anybody. I don't think anybody in this room, no offense, perhaps somebody will, but I don't think nobody will come up with relativity in this room. So I think we need to let go of that bias where we're thinking of scientific innovation as one individual sitting in one room trying to come up with one idea that changes the world, because that's just not how science happens. What happens is that even that one scientist is running over 15, 16 different ideas and experiments and then moving on and figuring out one works. So in general, I think we're going to see a lot more portfolio-led approach to scientific discovery and scientific innovation as well, which is that, hey, you have these agents that are just going ahead and exploring a vast problem space and coming back to the individual scientist and telling them this is what happened, what do you want to double down on, as opposed to a scientist individually specializing in one very narrow problem space, right? And I think this is already happening in how countries and nation states are starting to allocate money across scientific innovation. Some samples of the work: chemistry, large language models, cell to sentence for bio. Tool Universe is a great project where they're collecting a bunch of tools for scientists, because think of it as an MCP library, but for scientific tools in some sense, only for agents that do science. Experimental GPT for protein engineering, which was trained off of their GPT 4.0, and a bunch of expert, that's you can't see it, but it's basically a list of papers across the scientific workflow. So a bunch of work on collecting expert trajectories. what's next for me and like sort of this particular project at Lost Funk, we're actually now starting to like build these agents so that other people can use it. So specifically the hypothesis and the experiment planning agent, because that's sort of the easiest to get to be useful, which is like, hey, all of you all are scientists, you come in, you have an idea, you give it to this agent, the agent comes up with a set of hypotheses, comes up with a plan, it comes up with an agent.md file, and those three things go into a repo, and you can just pass it on to a Claude Code or a Codex and let them execute, right? So that particular agent piece, which is the hypothesis generation, experimental planning, is something that we're working on. And also simultaneously as we're working on that, because we're internally developing it with a bunch of the interns and fellows here, and they're using it for their projects, starting to collect a bunch of that data around expert trajectories. Hopefully we can use them to build benchmarks and evals later. So if you're a domain expert who wants to use LLMs and agents to automate their scientific workflows, please hit me up. I am not a domain expert, and I am curious, I would like to believe. So I'd be happy to have a chat and talk about how can we build those data sets and help you do it. That's about it. Thank you. Those are my socials. Happy to connect. That's me on social media. Like, that's what I look like. And yeah, shout out to Paras for being the coolest and giving me and everybody here the space to do stuff like this. Thanks.